Hey everybody, my name is Paul Reese, Android developer out of Boulder, also in the GDE program for IoT and Android. So just kind of out of curiosity, how many of you have done any sort of IoT development, either at home, work, or at an event like this? Okay, so a couple of you. How about Android? So roughly the same? Cool. So today I'm going to be talking about some of the tools and services available from Google to help make your Android and IoT devices smarter. While this presentation is mostly focused on Android things, I'm going to try to point out what would work with standard Android and Raspberry Pi development as well, just because Google's been sort of starting to run the gamut with machine learning and products and services. And I think it'll just kind of add a little bit more value for those of you that are taking your time to come see this talk. So with that said, we'll go over tools for image recognition, speech detection, and even some having conversations with your devices. Let's see, into the switch. Good enough, cool. So every decade or so, we see a big shift in technology that fundamentally changes how users interact with the world around them. For example, with the move to mobile first, we saw new ways to consume content and interact with services via apps on the mobile web. Jump forward to today, and we're starting to see the signs of the next big shift with AI and machine learning available in almost every kind of device, including mobile phones and connected devices in industrial, home, agricultural, and other environments. Given this, Google has spent the last couple of years building awesome machine learning tools around vision, speech recognition, and natural language processing for developers to use in their products. While some of these are cloud-based, others are able to run directly on the device, also known as on the edge, providing a variety of tools to fit your Android and IoT project's needs. So the first product I want to discuss is TensorFlow. So out of curiosity, how many of you have tried TensorFlow? So way more than IoT and Android. Awesome. For those of you who don't know, TensorFlow is a machine learning framework and the cornerstone of Google's offerings in image-based machine learning. It allows developers to train a model and quickly identify the subject of an image directly on the device or in the cloud. In addition to TensorFlow, there's TensorFlow Lite, which is an optimized version of TensorFlow designed specifically for embedded and mobile devices. So here we have an open source example of an Android Things device I put together using TensorFlow image recognition. In Boulder, because we're nestled right in the foothills of the Rocky Mountains, it's not uncommon for a bear or moose to wander out of the mountains and into downtown. So using a device like this one, we can place them along common paths and detect and classify an animal before it gets into a populated area. Once we have identified either a mountain lion, moose, bear, or elk, we can send the derived data to someone from Wildlife Services, allowing them to safely move the animal before either it or any people are harmed. If you're interested in this project, I have an older write-up for it on Hackster and with source code, and it's linked at the end of this presentation. I still need to go back and update it for TensorFlow Lite, though, so we can actually dig into that process now. So before you can start using TensorFlow in any application, you need to train a model that will be used for evaluating images. This can be done on your own computer by installing TensorFlow and all of the necessary dependencies directly in your machine, or by downloading a pre-built Docker image. Generally, the Docker image route is going to be easier, though they're both relatively straightforward to get you started. After you set up your environment, you need a lot of data to train against, as in thousands upon thousands of images, depending on what you're trying to classify. For my own projects, I tend to use a Chrome plugin to mass download images from a Google search. Once you have data, you'll need to sort it by its label into individual folders. With your data downloaded and sorted, it can be run through TensorFlow's retrain script to reuse some of Google's pre-done work in order to create your TensorFlow files, including a graph file and text labels. These labels will represent what your TensorFlow image classifier is able to recognize and will correlate with the titles of the folders from the previous step. One thing to note is that this process can take up to a few hours if you're lucky. So you'll end up seeing a whole lot of this across your terminal as bottlenecks are made and the data is analyzed. Next, you will want to process your graph file and optimize it for TensorFlow Lite. This will generate a TF-Lite file along with your labels. You can do this using the TF-Lite convert tool from a terminal, which will improve machine learning on devices with limited resources by trimming unused graph nodes, joining operations into more efficient composite operations, and switching from TensorFlow's protocol buffer serialization to flat buffers. Finally, you have multiple options available for integrating the TensorFlow Lite and label files into your Android or IoT applications. Currently, the most common way in Android and Android Things is to embed your files directly into your app and grab a few helper classes from the TensorFlow Android sample project. Once you have those helper files, you can use Android's Camera 2 API to know when a picture was taken, retrieve it, run it through the preprocessor helper to adjust the image's size, and then classify it with one method call to the classifier helper object. The setup process for this is a bit more involved than I can really show in a slide, but thankfully it's still relatively straightforward. So when you do look into this in the documentation, it shouldn't be too bad. Another option developers have for integrating machine learning into their Android and Android Things projects is MLKit for Android, which was just announced this last summer at Google I/O. MLKit is a collection of APIs that fit common machine learning use cases, providing a simple-to-use solution for beginners to machine learning to get up and running with. So the first feature in MLKit that we're going to discuss, as you probably have guessed, is TensorFlow. I feel like it's kind of the base of everything in these talks. So using TensorFlow through MLKit, you have a few options. You can either host your classifier file in the cloud or run them directly from the device. One thing that's really awesome about this is that you can actually support both. So as you update your models to the Cloud Console, your device can pull them down without having to update the entire Android app. And if the device does lose its internet connection, it can still work using previously downloaded models and the on-device TensorFlow API. In addition to TensorFlow, MLKit provides a few different options for developers to get up and running quickly with predefined models. So as you can see here, based on the icons next to the API names, some of these will run directly on the device, one will only work through a cloud API, and a few others support both options. So here we see a sample of the Labels API. This API will analyze an image and attempt to apply classification labels to the content, such as this coffee mug being held up in this example. When using the on-device API, you have access to just over 400 labels, whereas the online API has a broader set of categories and just over 10,000 different labels that can be associated with an image. Next, we have the text recognition API. When using the on-device API, MLKit can read Roman characters in both upper and lower cases, and then if you use the Cloud API, it allows you to read text off of documents and also recognize character sets from additional languages. So if you're familiar with the machine learning offerings from Google Play Services on Android, then this should look familiar. MLKit has incorporated the barcode reader API from Play Services in order to let developers locate and read the information from a variety of barcode formats, including UPC and QR codes. Likewise, the face detection API has been integrated into MLKit, allowing developers to detect multiple faces in an image, as well as landmarks on those faces, such as eyes and the edges of lips. Additionally, this API can attempt to figure out the expression on a face, such as smiling or frowning, or the probability that the subject's eyes are closed. One thing that's important to note, and mentioned a fair amount in the official documentation, is that this API is not face recognition, like we have in this example, but is only there to detect faces without attributing them to any particular person. So if you do want to expand into face recognition, there's additional steps that you would need to take after detecting a face that aren't provided by Google. So to give you an example of face detection being used in a real project, we can check out the sample from the IoT area at Google I/O this last year. These flowers contain a camera and will turn to follow the movement of a detected face in front of them. So additionally, they will change the color of their LEDs to reflect the expression of the user's face. So if they're smiling or frowning, or if they look kind of angry, it'll have colors associated with that. Finally, we have the landmark detection API. While this API is currently only cloud-based, it is able to detect a huge variety of landmarks, like Denver's Union Station seen here. So while Union Station isn't in and of itself a huge world-famous landmark, it is pretty cool to see that the API works with more than your big-name landmarks, such as the Golden Gate Bridge or Eiffel Tower. One thing that I haven't tried yet, and I'd actually be kind of interested to see if anyone else is willing to give it a shot, is to see if it's able to tell the difference between like the Disney Castle here in Orlando compared to Anaheim or Paris or Tokyo, or if it's able to tell the difference between the Eiffel Tower at Epcot versus the one in Paris. So if anyone wants to try that, I'd actually really appreciate knowing. So now that we know what MLKit can do, let's dive into how we can implement it. In this example, we'll focus on labeling objects in an image, though the way the MLKit, our Firebase MLKit API is set up, the same flow will apply to every sample that you just saw. The first thing we'll want to do is import the dependencies through your build.gradle file. MLKit is built on Firebase, so you'll need the core dependency as well as the MLKit specific dependencies. Next, you'll need to go into the Android manifest file and include the metadata related to the type of classifiers you would like to use in your product. So here we can see that we're including model dependencies for text recognition, face detection, barcode scanning, and object labeling. Although you can include the dependencies for multiple parts of MLKit, we'll actually only need the label value for this example. Once you're done with the initial setup, you can start using the MLKit APIs in your project. This sample uses the onImageAvailable callback with Android's Camera 2 API to access a media image, and will then run it through the Labels API. The first step in using an MLKit is gating the rotation of your image. This is important because an object must be faced in the same general direction as the trained models to ensure that the content is recognized. For brevity, the implementation of get rotation compensation is left out of this sample, but at the end I'll go over where you can actually find the full source code and grab that. Next, you'll need to convert your image into a Firebase Vision image object. While we are converting a camera image, the Firebase Vision image class contains multiple methods that can support changing images from a variety of sources, such as assets, input streams, and resource files. Once you have your Firebase Vision image, you can create an options object to customize how MLKit's API will work in your project. In this example, we're setting the confidence threshold for labels at 80%, so only labels that the API is fairly confident in will be returned to the application. Up next are Firebase Vision detectors, which are really where all the work happens. So here we can see that we're using a vision label detector. You'll need to create a detector object for every type of MLKit operation, though which one you use will depend on the API that you want to access. So however, as I mentioned earlier, all of these are pretty much going to work the same exact way. It's just going to be a different object depending on what you're trying to do with it. Finally, you will call detect an image on whichever detector you're using while passing in the Firebase Vision image object that you want to work with. This will allow you to add callbacks that can let you know if something goes wrong or return any pertinent information for the API about that image, such as labels or their confidence percentage. So now that we've covered a lot of the image processing offerings, let's talk about the Google Assistant. The Assistant is your entry point into speech recognition and natural language processing, allowing your users to control their device with more natural interactions. In order to talk to your device, you will need to first integrate the Google Assistant into your hardware project. The Google Assistant SDK enables you to embed the Google Assistant easily into most of your own custom hardware projects. Though currently Android Things doesn't have an SDK available, you can still add the Assistant to your Android Things projects by accessing the Assistant service directly using gRPC and a set of helper classes that are available in the Android Things sample project. This will allow users to not only ask about the time and weather, but also have custom voice options for your device. Some of you actually might recognize the cardboard thing on the right as an AIY voice kit. So what this does is it allows you to take a Raspberry Pi running Android Things or Raspbian and essentially turn it into a Google Home. So if you're interested in a more hands-on approach to learning machine learning on IoT, the AIY kits are pretty much a great way to get started. Using some of the predefined assistant actions, users can say, turn on, set the color to green, adjust the brightness to 65%, or a variety of other commands to directly control their device. Once the assistant has transcribed the user's command, it will be sent to the device in a nicely formatted JSON string, allowing the device to properly handle the request. So here we actually have a lamp that I recently 3D printed and worked on to demo some of these actions. So you can find a full tutorial of this at the end of the presentation as well if you want to see how everything works all together. So in order to add traits to your device, you will need to go to the Actions console and register your device, as well as declare the supported traits. You will then need to go into a terminal and register each individual device with Google via a unique instance ID. You can see here that we're registering an IoT device as a Lite with the option to control it with the on-off command. Then when the user says turn on to the device, this will be processed and returned to the device via the on-device action method as a JSON string if you're using Android Things, which then can be parsed and reacted to. In addition to the preset traits, the assistant allows your device to register custom actions. Take this range for example. It has a lot of options and control buttons as well as a display. By using custom traits, we can remove a good chunk of the buttons and add a single button that activates the assistant to allow users to give a custom command like set burner 3 to medium high or preheat the oven to 375, while keeping the display for showing device state. You can do this by creating a new actions configuration file, registering it with Google, and then checking for the new actions key value in the on-device's action method in order to respond appropriately. The Google Assistant also supports home automation via smart home integration with Home Graph. So Home Graph knows the state of all connected and registered devices. So when your user asks to dim the lights a little bit, or how many lights are on in a specific room, it knows how to respond intelligently. This feature is used by interfacing your own server with Google, allowing you to connect, control, and query devices through your existing infrastructure. But what if you want to support interactions that are a little bit more intricate? Dialogflow is a conversation engine that uses natural language understanding technology in order to attempt to process speech and perform actions based on the information provided. This engine is what also drives the normal interactions with the Google Assistant. If it doesn't have enough information to complete a request, it's able to continue a conversation with the user in order to fill in the gaps. So let's say, for example, that you have a few different products that can be offered as part of a home entertainment system. Your user can ask to speak with the home entertainment system and then say something like, put on Star Wars, dim the lights, and turn on the speakers. If your control system needs to know how loud the speakers should be or confirm which non-prequel Star Wars movie they actually want to watch, then you can request clarification to fill in the missing blanks, known as entities. Once Dialogflow has all the information needed to figure out the user's intent, it can send the entities to a webhook, like a Firebase function, which can then change device states using something like Smart Home or Google IoT Core. Finally, we have Google Cloud Machine Learning. The Google Cloud Platform provides a way for your applications to access machine learning tools remotely, taking the burden off of devices that may be very resource constrained. These tools are accessible through the use of a single REST API request. What's really nice about these tools is that they require no training data or previous machine learning experience. While this platform supports TensorFlow for custom machine learning, it also contains a set of ready-to-use machine learning models similar to the philosophy behind MLKit. If you're new to using machine learning on Google Cloud, I would actually recommend starting with these three for your IoT projects. So the Cloud Vision API is similar to MLKit image labeling, the MLKit labeling API, with some additional customization that can be done. Cloud Speech allows you to upload a raw audio file from your device and returns a text transcript of what was said in that file, similar to the voicemail feature on Pixel phones. And using the Cloud Translation API, you can send a selection of text to determine the language spoken, as well as translate to a different language. One of the fun things you can do is combine Cloud Speech with translation and text-to-speech, allowing you to make your own translation device, similar to the Google Pixel Buds. But really, you can do something way more awesome than the Pixel Buds, like this Porg toy that I hacked together to take anything said to it in English and repeat it back in Spanish. So actually, I'm going to see if I can make this work. I have no idea if audio is going to come through or not, though. Let's see, where's my mouse? We got a couple seconds here. I don't think we have sound, but I say, hello, how are you? And it says, hola, ¿cómo estás? So if you want to find that online, it's pretty awesome. Let's see here. Let me grab my mouse back here. Just to show how easy it is to actually use the Google Cloud for translating, I put the code for the Porg toy using Google's Python wrapper library for the REST API. A lot of this code is related to the electronic side of things and the AI-wide voice kit for interacting with the microphone and speakers. But the important parts to note are the translate client initialization at the top and the translate method in the middle of the loop that returns the translated text between one target language and the other. If you only want to translate input text and print it to a terminal or what have you, the main loop would be about 5 lines. So one really nice thing about Google Cloud Machine Learning is that there are Java and Python libraries already available that you can put onto your mobile apps or IoT devices that are running operating systems that support those languages. So now that I've touched a bit on the different options that you have for incorporating machine learning into your Android and IoT projects, you may want to dig deeper into how you can use these tools and services. To help with this, I have put together a sample Android Things project that uses TensorFlow Lite, all of the MLKit options, the Assistant SDK, predefined actions, and custom traits. I've also put together tutorials for everything discussed here today on Hackster.io. So any project we've talked about, any tech, it's all going to be there. If you would like to see more of what other developers are doing with Android things and IoT and machine learning, I also really suggest that Hackster link just to go see what the broader community is doing. To know more about anything that we've talked about today, you can check out the official documentation as linked here. So again, my name is Paul Ruiz, and thank you for coming to my talk. If there's any questions, I'll be around for a couple minutes. Otherwise, your best bet's going to be reaching me on Twitter there.